Salutations, many mathematicians. Now you know about scientific notation. We're going to do operations with scientific notation. No, we're not removing any kidneys. We are doing arithmetic operations, adding, subtracting, multiplying, and dividing. So our lesson purpose is to use the commutative, distributive, and exponent properties to efficiently add, subtract, multiply, and divide values written in scientific notation. So let's get started. You will want a calculator handy. Okay, so does 5 times 3 and then 2 times 8 equal 5 times 2 and then 3 times 8? If so, explain your reasoning and state which property is being used here. Well, if we take a look, 5 times 3 is 15, and 2 times 8 is 16, and 2 times 5 is 10, and 3 times 8 is 24. And if you notice, these actually have equal products. So what's going on here? Well, this is 5 times 3 times 2 times 8. And this is just 5 times 2 times 3 times 8. So what's happening here? This is the commutative property of multiplication, which tells you if everything's being multiplied, we can move around the order of the factors, the number being multiplied, and you will have the same product. So yes, they are equal. Maybe instead of saying they're equal, they are equivalent. Oh, that's such more mathy. We applied the commutative property of multiplication. Nice job there. Commutative property multiplication, as long as everything's being multiplied, you can change the order of the factors and the product is still equivalent. So the next directions say apply the commutative property and rewrite each problem by grouping the powers of 10. Solve using exponent properties and write your final answer in scientific notation. So it's really important. You can't just grab your calculator and put these in there. You have to show your work by how the directions asked you. Oh, really? Yes, really. Okay, so let's take a look at number 2. So number 2, notice this is set up the same way as above here. 5 times 3 is like 1.9 times 10 to the third, and 2 times 8 is like 2.4 times 10 to the sixth. So what did they ask us to do? They asked us to group the powers of 10. So since all these terms are being multiplied, I can rewrite this as 1.9 times 2.4 times, with our x, 10 to the third times 10 to the sixth. So again, what we're doing is we're grouping our powers of 10. So from here, you can grab a calculator and we can do 1.9 times 2.4, and we get 4 and 56/100 times exponent properties. Multiplying with the same base, we add our exponents. 10 to the 6 plus 3 is 9. Double check if it's in scientific notation. Your significant figure is greater than or equal to 1 and less than 10. And then your exponent here is an integer, so this is a great answer. Similarly, when we're dividing, what we can do is we can break this up into our significant figures and our powers of 10. What's nice here is that 7.2 divided by 3.6, well, we know 3.6 is half of 7.2, so this is 2. 7.2 is twice 3.6. Times, dividing with the same base, we subtract our exponents, or think there's 5 factors of 10 in the numerator, 2 factors of 10 in the denominator. 2 factors cancel out, and you're left with 3 factors in the numerator. And taking a look, yes, it's already written in scientific notation. Okay, I'm going to do number 6 with you also, because notice 6 and 7 are written a little bit differently. So when you get to 6 and 7, notice I don't have the second number or the first number written as a power of 10. So I want to rewrite this. So I'm going to just bring down the 3.1 times 10 to the negative third. Again, scientific notation needs that x. Times, and I'm going to rewrite 52 as a power of 10. So that's going to be 5.2 times 10 to the first. So now what can we do? Well, we're going to group our power of the 10 together and our significant figures together. So 3.1 times 5.2 times 10 to the negative third times 10 to the positive 1. I really like writing my exponent of 1 there. Maybe you don't, but it's very helpful for me. 3.1 times 5.2, again, grab that calculator, or maybe you can do that in your head. 16.12 times, add your exponents, 10 to the negative second. Oh no, our final answer isn't written in scientific notation. So what I'm going to do is I'm going to take this 16.2, I'm going to write that in scientific notation. So I would get 1.612 times 10 to the first. So that is equal to 16.12. I still have times 10 to the negative second as my value, part of my whole value. So then multiplying with the same base, you add your exponent for your final answer, 1.612, or 1 and 612 thousandths times 10 to the negative first power. Great. Go ahead and finish the page. So you're finishing 4, 5, and 7. Pause the video, finish 4, 5, and 7, and we'll go over them in just a second. Okay, let's see how we did. Okay, number 4, we should have ended with 2.45 times 10 to the third. I grouped my significant figures together, got 24.5. 10 to the fifth times 10 to the negative third is 10 to the positive 2, but that was not written in scientific notation. So 24.5 is 2.45 times 10 to the first, and then I added my exponents. Perfect. Taking a look at number 5, I grouped together my significant figures and my powers of 10, my orders of magnitude, earthquake, order of magnitude. And that's how I got my final answer. I didn't have to do any extra work from there. And number 7, again, rewrote 30 as 3.0 times 10 to the first. I broke up this with my significant figures and my powers of 10, and I got a final answer already in scientific notation because my significant figure is greater than or equal to 1 and less than 10. Cool. Let's keep going. So taking a look, now we're going to apply these skills we just learned to word problems, and notice that your answer needs to be written in a complete sentence and in standard notation. So standard notation, remember, is the decimal expansion. So we're not writing our final answer in scientific notation, we're writing our answer in standard notation, but we have to use scientific notation and exponent rules to solve. Okay, so let's take a look at number 8. Number 8 says, the human body uses red blood cells to deliver oxygen to the organs. An average adult has about 2 times 10 to the 13th red blood cells. Each cell is about 2 times 10 to the negative 5th meters long. If all the body's red blood cells were lined up, how many meters would it be? So remember, each cell is this many meters long. And this is how many there are. So what we're going to do, I like to think about a word like problem solving. So we're going to have the number of cells multiplied by the length per cell, or the length of one cell. So what do we have here? Well, the number of cells is 2 times 10 to the 13th power. And the length of one cell is 2 times 10 to the negative 5th power. So to rewrite these, we're going to have 2 times 2 times 10 to the 13th times 10 to the negative 5th. Notice I can use a multiplication dot, I can use parentheses to show this multiplication, but I have to use the x in between my significant figure and my orders of magnitude. From here, 2 times 2 is 4, times 10 to the 13 plus negative 5 is 8. We want our answer in standard notation, so we have to have our decimal equivalent. So the total length would be, so here's the 4, and then we need to move over 8 decimal places to the right. So that's going to be 1, 2, 3, 4, 5, 6, 7, 8. Count backwards by threes for your commas. And remember, this is units of meters. Meters. So that's hundreds, thousands, millions, 400 million meters in length. Oh my goodness. I don't know why you would line up your blood cells, but I mean, vampires would love it. Okay, so the next one, ooh, speed of light. So the speed of light is 3 times 10 to the 8th meters per second. If the sun is 1.5 times 10 to the 11th meters away from the Earth, how many seconds does it take that light to reach the Earth? We're getting old sunlight, you guys. It's not fresh. It took a long time to get here. So speed of light is super fast. Okay, so let's take a look. Well, we know that speed is, I think, of miles per hour. So it's distance over time. So from there, because we want to know how many seconds, we want to know about time. So what is the relationship of time with speed and distance? And maybe you've already looked at this in your science class, but if you didn't, we can always solve for it. So we can say speed is distance over time. And if we were solving by time for time, we can multiply by time on both sides. So time times speed is equal to distance. So then time is distance over speed. So time is equal to distance over speed. Oh, so we're going to be dividing, finding a quotient to answer this problem. So for here, when we are doing the math, well, what is the distance? Well, this is the speed and this is the distance. So 1.5 times 10 to the 11th. And the speed is 3 times 10 to the 8th. So we can just break this up like this if you want to with your parentheses. So 1.5 over 3 is 0.5. It's a half times 10. 11 over 8 is 10 to the third. 8 factors cancel out. There'll be 3 left over in the numerator. Notice this is not in scientific notation. If you want to write it in scientific notation, just 0.5 is 5.0 times 10 to the negative first. Then times 10 to the third is 5 times 10 to the second. And then to write our answer in a sentence, it takes 5, and then move the decimal over twice to the right, 500 seconds for light from the sun to reach Earth. And if you're thinking, well, about how many minutes is that? Well, remember, there's 60 seconds in a minute. So what we can do is we can take 500 seconds and divide by 60. And we know that's 8 1/3 minutes. So about 8 1/3 minutes. Wow, it's kind of a long time. It's going to take about 8 1/3 minutes for the sun to get all the way here. I guess it is a really far distance. Okay, so I would like you to finish 10 and 11. Remember, sometimes making a problem-solving plan of what numbers are going to be interacting and how can be really helpful for you. Go ahead, pause the video, finish 10 and 11, and we'll go over those in just a second. Okay, so number 10, here we want to know how many times wider is the hair than bacteria. So it's going to be hair divided by bacteria. From here, I got 3.4 times 10 to the first. So the hair is 34 times wider than the bacteria. We don't say meters times wider, it's just times wider because it's meters over meters, which would cancel out to make 1. So it's just how many times wider. Taking a look at 11, 11 is a great problem. You probably want to put a little star next to it. In the world. So we want to know how many times more people speak Chinese than English as their first language. So this would be Chinese over English. So when you do that math, you get about 3.36, 0.336 times 10 to the first. So the number of people who speak Chinese as a first language is about 3.4 times as many as the number of people who speak English as their first language. And if you said about 3.36 times, that's also fine. It's just typically when we talk about how many times something is, we talk about it in whole numbers or just to 1 decimal place, just to be as accurate and communicating as clearly as possible. Nice. Okay. Moving on to that last page. So the last page talks about, can the distributive property be used to simplify this sum, this addition? So remember, we've been dealing with commutative property with multiplying and dividing, and now we're going to look at adding and subtracting, and we're going to be looking at distributive property. So remember, distributive property says if you have A times X plus B, actually let's do X on the outside. X times A plus B is equal to AX plus BX. So thinking about this, we can go backwards. If you had 2x plus 4x, that's equal to x, because x is a common factor of 2 plus 4. Very interesting. Okay, so we want to know, can the distributive property be used to simplify this? Well, it is a yes. Distributive property can be used because both have a factor of 10 to the 9th power. So what we can see here is that we have 6 times 10 to the 9th plus 2 times 10 to the 9th. So here we can take this common factor of 10 to the 9th and factor it out. 10 to the 9th times 2 plus 6. And we looked at 10 to the 9th on the other side, so we can say 2 plus 6 times 10 to the 9th. And to end up this being 8 times 10 to the 9th power. So this is only true because they have the same order of magnitude. Only true if order of magnitude is equal. So I'm going to say 10 to the n is equal. You might need to rewrite expressions. Just like before, if the significant figure wasn't in the boundaries of greater than or equal to 1 and less than 10, we could rewrite it. Now we can rewrite it just to make sure that the order of magnitude is what we want by changing that significant figure. So we're going to be going backwards this time. So now it says, use the distributive property and exponent rules to simplify. Show all your work and write your answer in scientific notation. So here, notice we have the same order of magnitude, 10 to the 7th. So I'm going to factor out a 10 to the 7th, and what's left inside is 4 plus 8, because we had the 4 and then the plus and then the 8. And 4 plus 8 is 12, so I have 12 times 10 to the 7th. Oh no, it's not written in scientific notation. So from here, I notice that 12 is 1.2 times 10 to the 1st. I'm going to bring down that times 10 to the 7th. So I know that my final answer is 1.2, or 1 2/10 times 10 to the 8th power. 7 plus 1. Multiplying with the same base, add your exponents. Nice. Why don't you finish 14 and we'll go over the answer as soon as you're ready. Okay, let's take a look at how you did. For 14, we should have gotten 3.5 times 10 to the 7th. If you stopped at 35 times 10 to the 6th, it's not in scientific notation. Notice we have the common factor of 10 to the 6th, the same order of magnitude. 54 minus 19 is 35. 35 is 3.5 times 10 to the 1st, and then totally simplified, 3.5 times 10 to the 7th. Woo! Excellent. So the next question asks us, can the distributive property and exponent rules can be used to simplify this expression? What are we thinking? Explain why or why not. If not, explain in words how you can change the number so the properties can be applied. Well, taking a look here, not how it is written now. So I can't just say this is 5 plus 3 times 10 to the, I don't know, 4th, 9th, add them, subtract them, multiply them. I don't know. It's because it doesn't have a common factor that we can factor out. So not how it is written now. because 10 to the ninth does not equal 10 to the fourth power. We need to rewrite with the same order of magnitude, or 10 to the nth power. Orders of magnitude. Would you like an order of magnitude with that? Magnitude. Magnitudes? I don't know if that's grammarly correct, but we understand what we're trying to say. Okay, so what can we do? Well, we have 5 times 10 to the ninth power plus 3 times 10 to the fourth power. So from here, what do we want? Well, we want the same order of magnitude. So you can make it as both 10 to the ninth or both 10 to the fourth. So what I'm going to do is I'm going to break up the larger power. I'm going to break up the larger power into addends as the sum to make 9, but one of them has to be 4. So let me tell you what I'm trying to say. 5 times, I want this to be 10 to the fourth. But I also need to make this still to the ninth power, so that's 10 to the fifth. 5 plus 4 makes 9. And then we still have this, 3 times 10 to the fourth. So now, if we look at this, we have 5 times 10 to the fifth times 10 to the fourth plus 3 times 10 to the fourth. So we now have this common factor of 10 to the fourth. Okay. Well, then from here, we still need to simplify 5 times 10 to the fifth. Well, 5 times 10 to the fifth is 5 with 5 zeros. 1, 2, 3, 4, 5. Or 500,000 times 10 to the fourth plus 3 times 10 to the fourth. Now we have significant figures. I know this isn't written in scientific notation. 10 to the fourth and 10 to the fourth. So we can have 500,003 times 10 to the fourth power. Of course, we know this is not written in scientific notation, so we have to rewrite this as 5.00003 times 10 to the fifth, all times 10 to the fourth. So again, all I'm doing is I'm taking this value. It's not a significant figure because it's not meeting the criteria yet. So I rewrote it. And then I noticed that this ends up being 5.00003 times 10 to the ninth power. And it's written in scientific notation, and that's your answer. Now you might be saying, Mrs. Barth, how did you know? How did you know to rewrite them to have the lower power? Well, I didn't. And you can do the other way as well. I kind of ran out of room right here, so I'm going to do this problem again. But what I'm going to do this time is I'm going to rewrite them to both have powers of 9 instead of both having powers of 4. So here I rewrote them both to have a magnitude, order of magnitude 10 to the fourth. But now I'm going to rewrite them to both have a magnitude of 10 to the ninth. So I'm going to bring down this 5 times 10 to the ninth times, well, here I only have 3 times 10 to the fourth power. So I want this to be times 10 to the fourth. And to make 10 to the ninth, I'm going to multiply by 10 to the fifth. So this is making 10 to the ninth, but this was a 3 before. This was a 3 before. And now I'm multiplying it by 10 to the fifth, and it still has to equal 3. So what number times 10 to the fifth is equal to 3? That's going to be 0.1234 zeros and then a 3. Because if I move the decimal to the right 5 times, I get back to 3. So this value is equivalent. Okay, so whoops, you guys, I messed up here. This should be a plus sign, not a multiplying sign. My plus sign got too tilted. Goodness gracious, I hope you were yelling at your screen. Okay, so from here, I'm going to, oops, sorry guys. Oh, yeah. What am I saying? I was fine. Okay. So from here, what we're going to do is we are going to say, okay, 5 plus 4 is 9. So we have 5 times 10 to the 9th plus 0.00003. So there's 4 zeros, 1, 2, 3, 4, times 10 to the 9th. Now what you have is you have the same order of magnitude. So we can rewrite this as 5.00003 times 10 to the 9th. And it's already written in scientific notation, so that's our final answer. So again, you might find it more efficient for you to go to the larger exponent. You might find it more efficient for you to go to the smaller exponent, but you do need to have the same order of magnitude to be able to add and subtract in scientific notation. So the rules is if you have a times 10 to the n plus b times 10 to the n, that becomes a plus b times 10 to the n. And if you're subtracting, well, as long as you have the same order of magnitude, a minus b times 10 to the n power. Nice. Okay, so I'm going to do 18 with you. And I'm only going to do these problems one way because, we're not going to make this video last forever. Okay, so we have subtracting. Oh no, we don't have the same order of magnitude. So I'm going to choose to keep the bigger order of magnitude, so 10 to the negative 5th. So I'm going to bring down 8 and 41/100ths times 10 to the negative 5th minus, and now I'm going to break up 10 to the negative 6 into 10 to the negative 1st times 10 to the negative 5th. So I have this negative 5 and I have this negative 5. So remember, this value here is equal to 7.9. Well, what times 10 to the negative 1st is 7.9? You are correct. Oh, sorry. 10 to the negative 6 is what we broke up, so we just bring down the 7.9. So from here, we have 8.41 times 10 to the negative 5th. And now what we need to do is we need to rethink what is the 7.9 times 10 to the negative 1st, and that's going to be 0.79. So I have times 10 to the negative 5th. So here we have the same order of magnitude. So we can look at this as 8.41 minus 0.79 all times 10 to the negative 5th power. If you grab your calculator and do that subtraction, you get 7.62, and it's just times 10 to the negative 5th. Double check your answer is in scientific notation and give it a box. Awesome. Go ahead and finish 17. Go ahead and finish 17, and we will go over the answer in just a moment. Okay, so taking a look at 17, I decided to rewrite them both with the power of 10 to the 4th. So from here, I rewrote 10 to the 6th as 10 to the 2nd and 10 to the 4th. I noticed that 4.12 times 10 to the 2nd is 412. So then when I added these together, I got 415.94 times 10 to the 4th. And then I had to rewrite that in scientific notation, add my exponents, and I got 4.1594 times 10 to the 6th power. Again, you don't want to lose any of those digits. They are really important to the final value of your number. Great job, mini mathematicians. Excellent work. I will see you next time. Stay psyched, do your best, and be nice to everyone.